One of the first discoveries of modern chemistry dates to the year 1662. It was made by Robert Boyle, who relied on the work of Henry Power written a year earlier. By experiment or reading, you are probably familiar with what we call Boyle's law. At constant temperature, the pressure of a sealed gas is inversely proportional to the volume. It's easy for us to imagine why the pressure goes up as the volume goes down. Look at this diagram of a syringe filled with air. As you push down on it, the molecules have less volume to move around in. They hit the walls more often. As the molecules hit the wall more frequently, we feel more push, and it gets harder to compress the gas. When we graph pressure versus volume, we see that as the volume gets smaller, the pressure gets larger. When we graph the reciprocal of pressure versus volume, we see a direct proportion. As the volume increases, the reciprocal of the pressure increases. This means that the product of the pressure and volume of a sealed gas at constant temperature does not change. P times V is a constant. To solve problems with this powerful law, we need to do a little simple math. At any point on the pressure-volume curve, P times V is a constant. That means at this point, which we call V1, P1, the product is the constant K. At this second point, which we call V2, P2, the product is the same constant, K. Since the two products are equal to the same number, they are equal to each other. So we can express Boyle's law as P1 times V1 equals P2 times V2. Now let's use this relationship to solve a problem. A sealed gas at 2.5 atmospheres pressure has a volume of 130 milliliters. What would the volume of the gas be if the temperature stays the same and the new pressure is 4.0 atmospheres? First, we write the two-point expression of Boyle's law we saw earlier. Now we are looking for the new volume, which we call V2. We can solve for V2 by dividing both sides by P2. V2 equals P1 times V1 divided by P2. Now we substitute the given values for P1, V1, and P2 into this relationship. We see the pressure unit, atmospheres, divides to equal 1, leaving us with only the volume unit, milliliters. And the new volume is, to two significant digits, 81 milliliters. Suppose instead we use the same system and ask what the pressure would be if the volume expanded to 210 milliliters. We write the expression of Boyle's law and solve for the new pressure, P2. We see that P2 equals P1 times V1 divided by V2. Plug in the values of P1, V1, and V2, and we see that the new pressure must be 1.5 atmospheres to 2 digits. Boyle's law gives us the tool we need to find any pressure or volume of a sealed ideal gas, as long as we know the starting pressure and volume, and as long as the temperature stays constant.